Hey there, physics enthusiasts. Today I'm taking you on an enthralling journey from classical radiation theories all the way to quantum statistics. Buckle up, because it's going to get fascinating. First up, let's talk about classical statistical mechanics. This branch of physics deals with how particles distribute themselves in different states of a system using classical mechanics principles. Think of a gas in a container. Classical statistics help us predict properties like temperature and pressure based on particle behavior. Now let's dive into the classical theory of radiation. This theory primarily revolves around blackbody radiation, which is the perfect emitter and absorber of radiation. According to classical physics, the energy emitted by such a body is proportional to the temperature raised to the fourth power. However, there was a problem known as the ultraviolet catastrophe, where classical theory predicted infinite energy at short wavelengths. Clearly, something was missing. Enter Max Planck. In 1900, Planck proposed that energy is quantized, meaning it can only take on certain discrete values. This was the birth of quantum theory, which resolved the ultraviolet catastrophe and laid the foundation for quantum mechanics. All right, here's where it gets even more intriguing: quantum statistics. Unlike classical mechanics, quantum mechanics considers particles as indistinguishable and subject to the Pauli exclusion principle, or Bose-Einstein condensation, depending on the type of particles. Let's start with Bose-Einstein statistics. This applies to bosons, particles that can occupy the same quantum state. Imagine a bunch of particles behaving like a single entity. That's Bose-Einstein condensation. Superfluidity in liquid helium is a prime example of this phenomenon. On the flip side, we have Fermi-Dirac statistics, which applies to fermions. Fermions, including electrons, protons, and neutrons, obey the Pauli exclusion principle, meaning no two fermions can occupy the same quantum state simultaneously. This principle explains the structure of atoms and why matter doesn't collapse into a point. To sum it all up, classical statistical mechanics gave us a way to understand macroscopic properties from microscopic behavior, but it had its limitations. Quantum statistics with Bose-Einstein and Fermi-Dirac distributions provided the tools to navigate the subatomic world where classical theories fell short. Isn't it amazing how the universe works? From the predictable world of classical physics to the mind-bending realm of quantum mechanics, we've come a long way. And who knows what new discoveries lie just around the corner. Thanks for joining me on this whirlwind tour of classical radiation and quantum statistics. If you enjoyed this video, don't forget to like, subscribe, and hit that notification bell so you never miss an update. Until next time, stay curious.